It's mind-blowing to see how many students keep goofing up this derivative problem below. And that doesn't have to be you anymore. So if you want to crush this like a ninja, stick around until the end. So we do this the right way. For x squared plus y squared equals 1, the problem that many students make here is they approach this as you normally would for finding the derivative of a function. But we don't have a function here because this is the equation of a circle, which is only a relation, not a function, because it fails the vertical line test. But let's go ahead and do this anyways and take the derivative the wrong way that many students do, so we can see why that method doesn't work, and I'll then show you the proper way of doing this. So what we'll first try is we'll simply subtract x squared on both sides of the equation, giving us y squared equals 1 minus x squared, and then after taking the square root of both sides, you'll be left with y equals plus or minus the square root of 1 minus x squared. Do you already see the issue of trying to take the derivative of this? If you don't, that's okay. Let's move forward. The first thing I want to do is I want to rewrite the radical here as a power. That way, when we take the derivative, it's a little bit clearer to see how the chain rule is going to work. And if you don't remember the chain rule, that's okay. I've got a video for you. But remember that you simply then take the derivative of the outside function times the derivative of the inside. So for the outside, we bring the old power of 1/2 out in front, and then we subtract 1 from it, leaving the inside intact. And then we multiply all of that by the derivative of the inside, which would just be negative 2x. And when you simplify this further, the plus and minus 1/2 times negative 2x reduces just plus and minus x. And then for the negative 1/2 power, I want to rewrite it as a radical here on the denominator. And already the issue with this derivative expression is that you do not get a one-to-one mapping. It's a bit ambiguous because if I put in a value of x, there are two possible values for what the slope is. So that doesn't really work, and there are other ways you can manipulate this by going back to the original equation, treating it as a piecewise function where you work with the top arc of the circle and the bottom, and I'm not going to do that here, but let's work with the better and clearer way for how to find the derivative of this original expression. This is where your teacher may have mentioned implicit differentiation. And so for methods like this, where you have to deal with a relation between y and x because it's simply not a function, you got to approach this a different way. And so I might not be doing this exactly the way you've learned, but this is a way I've known to not fail me because it makes it really easy. So what I want to do is I want to take d over dx of both sides here, and I want to treat d over dx as almost something I'm multiplying the x squared and the y squared by. And so when I distribute it through, it might look kind of janky, but what I'll have here is for the x squared term, normally when you take the derivative of x squared, many of us will say, oh, it's 2x. Well, that's not fully precise because it needs to be with respect to a variable, right? So the derivative of x with respect to x of x squared, yes, it's 2x. But what I'm going to do here is because I took the derivative of an expression x squared, where there was an x there, I'm treating that as the control. And for this d over dx, I'm going to just rewrite it as dx over dx. So the numerator tells me what variable I treated as the control. So in x squared, I treated x as the control. I'm now going to add this to doing the same thing where I distribute the d over dx to the y squared term. And so the derivative of y squared, it doesn't change with respect to x normally, right? It would be treated as a constant. But here for implicit differentiation, we're going to treat it as a control variable, y, as if it was with respect to y when we take the derivative. So the derivative of y squared with respect to y would be 2y. And then for this term, this d over dx, now on the numerator, I'm going to use the letter y because for the expression y squared, I treated the y as the control variable in this case. And then for the right-hand side, the derivative of 1 with respect to any variable we know is 0. Now, the reason why I do this method is it's very clear to me when I simplify this expression to see what term is going to end up with the dy over dx. And I've taken differential equations, and maybe some of you haven't, and that's okay. And this is a method we used in the upper level math classes, but it's totally okay to use here because you're going to now see something really cool. You might be wondering, what are we going to do with this dx over dx? You might be thinking, Dave, that doesn't even make sense. It just complicates things. And I wouldn't blame you for that. But the cool thing is that for dx over dx, think of a variable and how it changes with respect to itself. It's 1-to-1, right? So dx over dx is 1, and that just goes away. And now we have an expression that's a lot nicer to work with because only one term here now has dy over dx term. And so what I want to do next is I want to isolate the dy over dx by itself. So in other words, I want to solve this equation with respect to that so it's on the left side. So what I'm going to do next is subtract 2x on both sides of the equation and then divide 2y by both sides, leaving me with this really simple expression dy over dx equals negative x over y. And stick around for a bit because we're not quite done here, because students need to really be careful with this final answer. So when we look at the graph of the circle that we started with, x squared plus y squared equals 1, what does d over dx equals negative x over y tell us? What it's telling us now is that if you are at a point x, y, and you plug in both the x and y values into that equation, so for negative x over y, you now have a one-to-one map for the slope. And so tell me below what the slope is going to be at the following points: 0, 1, and 0, negative 1. Okay, so you should recognize that if I plug in either 0 for x and 1 for y, or 0 for x and negative 1 for y into that expression negative x over y, as we expect, the slope here is 0 because the tangent is just a horizontal line, and a horizontal line has a slope of 0. Now, notice also that we're domain restricted here, and students often miss this. Y cannot be 0 here. And I want you to tell me below why that's the case.